So why physics? Well, physics is probably most familiar to you through people like Einstein and studying the Big Bang and atoms and so on, electricity, magnetism. But it's actually a lot more than that. If you looked at that pre-presentation, there was a lot of interesting things in it that you don't normally think of as physics. So for instance, there were um, murmurations of swallows. So those patterns of birds in the sky that you see sometimes, physicists study that because we like studying patterns. We study global warming. We have quite a few physicists in the physics department that study neurons in the brain. That's a field called biophysics. There are papers published on the stock market in our main journals in physics. So we develop models for anything we want, basically, and we publish them in physics journals. And a lot of physicists go off to start hedge funds and investment companies and things like that. So why is that? Why do we apply what we know to so many different areas? It's basically because physics is embodied by a simple strategy, and that is to break a problem down into as basic principles as we can do and then analyze it basically in a sort of logical way. So other fields of science do things a little bit differently. Biology tends to look at things a little bit more sort of holistically and has a lot of complicated detail in it that is really hard to break down to basic principles. In physics, we sort of look at problems and break them down into, say, fundamental laws and things we know about them. So what do you learn when you're doing this? Well, you learn how to reason with numbers, so make predictions and just understand what numbers mean and what statistics mean. You learn how to write programs to analyze data. So that's a really useful skill for very many different jobs. And you learn how to communicate those ideas. So not everybody understands science as well as people who go into physics or people who become physicists. And so you still need to communicate those ideas to other people. So we teach all of those things. And because we do a pretty good job of that, physics majors have a very high employment rate in Canada. So this doesn't get updated every year. This data is from the Canadian Association of Physicists from 2017. And what they showed is that people with an undergraduate physics degree have an employment rate of 98% just a few years after their degree. And then if you have a graduate physics degree, you have an employment rate of 99%. So those are much higher employment rates than the general population, and even perhaps the general population of university trained people. Where do these graduates end up getting jobs? So places you might suspect, like research and development at companies, computing, but also quite a few other areas. So one of the things about physics is that it feeds into a wide variety of jobs. It's really hard to point to one particular sector that just snaps up every physicist. They end up going into a wide variety of areas: consulting, sales and marketing, health sciences, teaching, and so this other area is a big one, and it itself is broken up into many different subjects, including journalism, so being able to interpret science, as I said, finance, I already mentioned, meteorology, the prediction of weather, in other words, law. So many patent lawyers have physics trainings, and of course, like starting up companies, tech startups, and so on. So we don't have salary information for Canada, so we had to go to the American Institute for Physics. So these numbers in this graph are in American dollars, but it compares the salary for people who just graduate with a bachelor's in these fields, right? And starting off with biology at the bottom at somewhere between 30 and 40,000. Going up through the list, you have chemistry, accounting, nursing, civil engineering. So we're starting to pass engineers, mechanical engineers, mathematics. It's a little surprising. Chemical engineering, electrical, and then there's physics. And so again, remember I told you there's just this wide variety of jobs that physicists get. And so you can see there's a big spread in the incomes that people earn. And the part of that is just a matter of choice. You might go into a field that just doesn't pay as well as other ones, and that's a choice you make. But you can see that the average is actually one of the highest, only really outpaced by computer science and aerospace engineering. If you convert this average salary and include inflation, and converted into 2020 Canadian dollars, it's $83,000 per year. So that's not a bad salary for a undergraduate degree. So let me tell you a little bit about the program at the University of Ottawa. It's a fairly sizable department in the sense that it has quite a large number of professors, 30 professors. We all have PhDs. There's a couple options that you can focus in. So you could just do an honors bachelor's in physics. That's one option. But you can also specialize, and you end up with these titles on your degree because you've taken more courses in these specializations. So one of the things is biophysics. So as I said, for instance, studying neurons or how cells behave, those kind of things. And the other one that we specialize in at the University of Ottawa is photonics. So that's using light to, say, do telecommunications or computing or sensing. I'll tell you a little bit more about it later in the talk. We also have a joint degree with mathematics. So this is completely joint between the two departments. So if you're more interested in math, but still like seeing how it's applied, then that's a good option for you. We have a dual degree. So this is a really unusual thing. I'm not sure there's any of these in Ontario other than this one, where you actually earn both a bachelor's and bachelor's of applied science in electrical engineering. So two full degrees. And the reason why we can do that is because physics and electrical engineering overlap quite a bit. So there's a lot of courses that you would be taking with physicists if you're an electrical engineer. So we just count those towards both degrees, and then you just need to do one extra year to make up the courses that didn't overlap. And that gets you 2 full degrees. That lets you, for instance, go on and do research if that still interests you, because you have that physics degree, and in particular, you get quantum mechanics. And it gives you that degree that employers like for particularly for electrical engineering jobs. And for all of these options, you can do co-op. So co-op is where you have scheduled into the degree times off where you get jobs with employers, and that's arranged through the university. So there's a whole co-op department in the university that helps arrange that, and it's fully accredited. Okay, so just to go through the details of what an honors bachelor's degree in physics looks like. And this is kind of universal across North America, in fact. So usually you take 2 semesters of physics courses in your first year, 2 calculus courses, so 2 semesters of calculus, a computer programming course, a math course in linear algebra, and then you still have 3 to 4 elective courses you can take on top of that. And that 3 to 4, 2 to 4, I'd say, stays there for the rest of the degree. So every year you have a few courses that you can take per year that are elective. So if you go on from that first year, and then you get some more specialized courses. So starting off in second year, you can start taking astronomy, electromagnetism, thermodynamics teaches you how engines work and the laws and how solar panels work. Quantum mechanics, so that's the science of atoms and single particles. Optics, so one thing that's unusual here is because we have a photonic specialization, we start teaching optics in second year. One of the things that really distinguishes us from a lot of other universities in Canada is our ratio of students to professors. So we have 30 professors, and usually we admit somewhere around 80 students or so. So even in that first year, we have this nice 2 to 1, maybe 3 to 1 ratio of students to professors. And what that allows us to do is it allows us to offer those students very unique training experiences. So for instance, I usually host 1 or 2 students per year, undergraduate students per year in my lab, where they come and do research with me for up to a full year, actually. And so we have some really top labs in various areas like photonics, biophysics, and material science, and these students get to work directly with us doing research. So we try and get you involved in research, not just learning about the subject, but involved in what actual science is as quickly as possible at the University of Ottawa. And then as you go into later years, you'll be doing things like have options to take courses on lasers, astrophysics, general relativity, so that's black holes. Quantum field theory is the theory behind particle physics, basically. So all of these things you can start taking in the third and fourth year. Most of these courses, particularly from year 1 to 3, are offered separately in French and in English. And you can sort of move back and forth between those courses freely, or you can get a special designation on your degree as like a French specializations if you take a certain number of courses in French, or if you're French, you can get an English specialization. That's also a possibility. But really, you know, if you don't do that, you just can take French or English as you wish. Up in the fourth year, then we alternate between years, which ones are offered in French and English. So just to show you what the calendar would look like in a little bit more detail, I've already sort of gone through first year physics. And second year, you start taking more math courses, waves and optics, that's what I'm teaching this year, mechanics, so that's really teaching you about how, you know, mechanical systems work, and circuits, designing circuits, electricity, magnetism. You start taking modern physics in second year, so that's learning about special relativity and quantum physics. And then you go on and take things in third year like theoretical physics, thermodynamics, and so on. And you can see here, there's 3 elective units there, 6 elective units. So 3 units is 1 course. And again, there's lots of opportunities for electives throughout the degree. And those can be, some of those have to be in other faculties. So sometimes you have, like for instance, here you can see you have to take a course out of arts, education, law, or social sciences, but most of them actually are not really prescribed at all. There's no restrictions. And then we have these specializations. This is like, for instance, the photonics option, but we also have one called the biophysics option. And really, it just trades in some of those electives and makes sure that you take the courses that are related to photonics. So by third year, for instance, you might be taking Introduction to Photonics, obviously. You might be taking the lasers course, or you might be taking, you'd have to take the waves and optics course. So, so that's sort of how those options go. And you don't really need to decide on those before third year, actually. So you can sign up for them right away. If you're sure you want to do a photonics option, you can sign up for it right away. But you can also switch into it later. One really cool course that we launched a couple of years ago that's been really successful is called the X Projects course. It's taught by a fellow named Andrew Pelling. He's a TED fellow, so you've probably heard TED Talks, but most of the TED Talks are actually TEDx talks. There's very few real TED Talks, and he's one that actually gave a full TED Talk in New York City about printing ears, so human ears with a printer. So he prints a scaffolding for cells out of apple cells. So he calls himself a biohacker because he repurposes technology and uses it in biology. So he's teaching people to sort of take that method and learn how to sort of do a whole bunch of different things. So for instance, like get drones to measure air quality across the city. Do sort of pattern analysis with cameras and bee traffic, do room mapping with ceiling lights, really cool ideas. So this is really to sort of get students, again, more engaged in doing things rather than just learning subjects. So the whole university has one of the biggest programs, I think maybe the biggest co-op program or second biggest co-op program in Canada. And the physics department among that has an extremely high placement rate. So, you know, maybe we have 4 or 5 people per year, up to 10 people per year going into co-op. And the last time I checked was 2017, and we had a 100% placement rate for years before that. And that's basically because physics students are good and employers want to hire them. And so it's not so hard for them to get jobs as part of the co-op program. So you earn money as part of that, so that can help pay for your tuition, because it is a job. You have to earn at least minimum wage. And there's a wide variety. So University of Ottawa has a sort of unique position amongst universities in Canada because we are in the capital, and there's a lot of things that are in the capital that you have access to. So, for instance, of course, there's the federal government. So there's all sorts of departments that have hired our students, including Environment Canada, to do research or testing of environmental things like, for instance, for engines or air quality. Health Canada, Industry Canada, place I used to work, the National Research Council, which is Canada's national lab. So it's a gigantic lab system. So there's lots of research happening there. And then there's also lots of private companies that have their headquarters in Ottawa, including Mitel and Sienna. I think Xerox has its headquarters in Ottawa. Triumph is an accelerator at the University of British Columbia. And I put that there just to point out that we don't just place students in Ottawa, we place students all over Canada, in fact, all over the world. So if you see an opportunity that you want to take advantage of somewhere else in the world, you can do that as part of your co-op. And lots of people have, actually. And as well, you can do your co-op as a research position in a lab at the University of Ottawa. So I almost always have a co-op student in my lab. I have one right now, for instance. Right. So I talked a little bit about this before, the dual degree. It's a 5-year program, and you can still do co-op as part of it. So co-op always adds 1 year to your program. So this would add another year to this, and that make it 6 years. And you end up with these 2 degrees. So you end up with a sort of recognized engineering degree, right? So engineers have these accredited degrees. They have a very standardized system for producing engineers so that everybody knows what they can do. Employers will know exactly what an electrical engineer is. But then you also have access to the wider set of career opportunities that physicists have, in particular for research. Yeah. So the university really specializes, physics at the university really specializes in these 3 areas. So we teach everything. So we teach, particle physics, and we teach general relativity. But these are really what we specialize in. So one of them is the biophysics. So here are those ears I told you about, the scaffolding of apple cells used to grow human cells on to make a replacement ear, printed with a 3D printer. So this is Andrew Pelling stuff. But also looking at like how cells respond to stress, actually making new types of medical sensors, studying the brain and how it works. And then also studying how to make new types of tests and instruments using microfluidics. So those are little tiny tubes made out of on glass chips. So it's trying to make a whole lab on a chip. And then something we've gotten into in the last 5 years in a big way is material science. So this is trying to make totally new materials that aren't available in nature. The hottest one has been for the last 15 years, graphene, and we're strong in this area. So graphene is a single layer of carbon atoms, and it's incredibly strong and has just all these very unusual and important properties that will mean that it's going to be used in a lot of technologies in the future. We also make quantum dots. These are artificial atoms, and we do a lot of nanophysics. So it's actually sort of studying what happens if you place down atoms or very small structures that are much smaller than a micron. And then lastly, in photonics, we're probably the best university in Canada. And this is partly due to the history of photonics in Ottawa. So Ottawa was home to, well, first of all, the federal government did a lot of research in photonics, and then it was home to Nortel. And Nortel did a lot of research in photonics as well. So photonics is using technology with light, basically. It's trying to make devices with light. And the biggest example of that is optical fibers. We send pulses of light over optical fibers. We lay these optical fibers under the ocean and from city to city, and that's what carries our internet. And Nortel had a big part in developing that. Unfortunately, Nortel went bust, but what most people don't know is that all of their research labs stayed intact and were bought up by other companies and are still operating. And in fact, they're driving the success of those companies. So Sienna is one of them, for instance. Sienna is a big player in photonics around the world. And the Nortel labs gave them their next generation of technology, which kept them in competition. But also things like environmental sensing, so sensing like pollutants um, or explosives from far away using lasers, and then trying to do information processing with photons as well. I use photons to study quantum mechanics and trying to make quantum computers, for instance. This is where my lab is. So the physics department, the research of the physics department is really split between two buildings. This one, the Advanced Research Complex, and then across the street is the STEM building, which I'll show you in a second. So this is a well, it was built in 2014. So to me, it's still brand new, but it's 6 years old now. And it was state of the art. So it has vibration isolated labs. In fact, many of the labs are buried into this hillside just to make them vibration isolated. So really amazing building to do research in. And a lot of those research positions are, the undergraduates would be in this building. There are no classes in this building, but this is where they would be meeting their profs and working in the research labs. This is the STEM building. So this is the building in which a lot of the physics classes would be in. And this is the home of the physics department in a sense that this is where our office is, where students would have contact with the administrators in physics and so on. And so this is even newer. I think it's just a couple years old, maybe 3 years old. It's $115 million. And what we did is we grouped together all of the STEM sciences. So science and technology, engineering, math are all in this building now. And that lets us do a lot more interdisciplinary stuff, including having a big maker space. So this is a big space with 3D printers, laser cutters, machining tools, where students can learn to build things and invent things. This is what it looks like on the inside. One of the things we're proud of here is that we have these big glass sort of meeting areas in the middle where people work on projects with companies. You learn about patenting and things, venture capital. So if you're interested in sort of the engineering and application side of things, this is really great opportunity to learn about how things really work, particularly if you want to start up a company. Yeah, so this is again what it looks like inside. Down on the sides here, you can actually look down onto some of the big research labs, and in the back here, these yellow areas are these interdisciplinary sort of collaboration rooms. And I think on the right there, that's actually supposed to be, that might be the machine shop. So the physics department has a pretty vibrant student life. We have a physics society that organizes regular, say, events. These could be trivia nights. We have one that's regular called Pizza and Prof, where you get to talk to profs in an informal, or one prof in an informal atmosphere while you get free pizza. There's a physics fest where you get to learn about all the research in the department and have free food as well, and movies and so on. And we also usually organize, there's a broader science association, the Science Student Association, that organizes sort of bigger things like a job fair. We also organize a job fair in the physics department, actually. Science talks and conferences and so on. So I'm coming to near the end of the talk. So I'm just going to re-emphasize why physics is a good degree to get. And one of the things that might surprise people is how it really keeps doors open for students, because the physics degree really gives you a very strong foundation in reasoning and logic and just understanding problems. And evidence of that, this might be surprising, is that the MCAT exam, so the MCAT exam is the medical entrance exam in the United States, and most Canadian universities use it, although not the University of Ottawa because it's not available in French. So most universities use MCAT scores to help decide who gets into medical school. If you look at how the degrees score on those MCAT tests, you might expect that pre-med would be up near the top, since that's actually teaching you what you need to know to get into medical school. But instead, tied for the top are physics and biomedical engineering. And so biomedical engineering you might expect to be up there, but physics is a little bit surprising. So we have the top scores on the MCAT in pretty much every category too. So not just like physical sciences, we also get really high marks in biology and verbal reasoning. So you might not expect that. So that's basically because we have very good students and because we train them very well. But the MCAT's not the only example. We really ace every exam. So the GRE is the exam that the United States uses for students going to graduate school. So that's if they want to go on and get a PhD. This is the exam that they look at to accept PhD students. And we have the highest of two of the three categories. So combined verbal and quantitative scores of any degree, undergraduate degree. The GMAT exam is the entrance exam for business school, and we have the highest scores of any major in that. And the law school exam, we have the second highest entrance scores for that. So a physics degree really opens up a lot of doors for people. I'm not saying that you should do a physics degree if you want to become a doctor. If you're really set on becoming a doctor, maybe you should do biology. But if you are really interested in physics and you want to become a doctor, then doing a physics degree is not going to stop you. It might even help you become a doctor. So I told you why you should do physics. Now, why should you come to University of Ottawa? So I've summed it up in 5 reasons. So one is we give our students a lot of research opportunities, and that's because we have an amazing professor to student ratio, much better than most universities. We have bilingualism, so we're one of the largest bilingual universities in the world. All of our undergraduate courses are offered in French and English separately. And so you can choose to move back and forth as you wish.